Okay, let's talk about this concept of equilibria a little bit more. So, what exactly does that idea equilibrium mean? Why is the concept of equilibrium so important in chemistry and in biochemistry? Well, let's consider a couple of examples, right? So, consider in the blood the following reaction where carbon dioxide plus water forms carbonic acid plus protons. Super important, basic chemical reaction going on in your blood. We're going to talk about it again later when we talk about um, oxygen metabolism. So why then does adding more CO2 make your blood more acidic? And by the same token, why then more acidic in the microvasculature? Why then does adding protons, as happens in the lungs, cause more CO2 to be released, right? So here's another example. If you consider mixing oil plus water, you guys probably know they don't like to mix well, right? But maybe what you don't realize is if you do that very slowly with very small amounts of oil, initially the oil will disperse and be completely solubilized in the water. And it's only after you get past a certain point that the oil will separate from the water and you'll get that clear phase separation that you're used to and saying oil and water don't mix. So why is it when adding something on one side of a reaction like this, things move? The distribution of reactants and products change, right? So the spontaneity then of a process, remember that's what we're sort of thinking about here in this lecture, is the spontaneity of things. Depend upon a set of conditions that are linked to this intrinsic balance between the two sides of a reaction or a chemical reaction, the way we tend to write them, right? And when no net change takes place, right? When there is no difference between the reactants on one side or the other of a reaction, and concentrations don't change significantly, that's when we say the process is at equilibrium. And we know from the discussion we just had that under that set of conditions, the free energy change equals 0. That free energy condition, right? And the idea that the reactant product relationship is in balance, these ideas are linked to each other through the concept, of course, of the equilibrium constant, which gets the symbol KEQ. Okay, now there's a very important relationship between free energy and the equilibrium constant that you guys need to know, or if you don't know it, you need to know it. If you've forgotten it, you need to remember it. And it looks something like this, where delta G naught equals minus RT log, natural log, of the equilibrium constant. Super important relationship in biochemistry. And we're going to see it over and over and over and over again. And a couple of things here, right? So I wrote that down and I snuck in this funny little knot in there, right? So where'd that come from, right? The other thing I sort of snuck in here on you is the relationship between this free energy balance and the equilibrium constant depends on the logarithm of the equilibrium constant, the natural log. Why would that be, right? So, and that's just a reminder to everybody, R, this capital R in these expressions, of course, is the universal gas constant. Hopefully you guys remember that. Okay. So consider the following expression for an equilibrium, just a generic equilibrium. Let's start with, say, A moles of a reactant A that converts to B moles of a product B, right? And we know we have an associated equilibrium constant, right? And we remember, hopefully, from our high school chemistry, that that equilibrium constant is defined, or can be defined, as the balance between the products and the reactants, or more specifically, the concentration of B, or the moles of B relative to the moles of A. Written out, that looks something like this. The equilibrium constant is equal to concentration of B raised to the B divided by the concentration of A raised to the A. Okay, so the other thing that I sort of alluded to here, and again, you hopefully remember from your high school chemistry, is that if we have a reaction, like my bicarbonate CO2 reaction here at the top, or this reaction here, if I add more A to this reaction, if I put more A in, the reaction is going to make more B, right? Likewise, if I added more B to the reaction initially, the reaction is going to go this way. It's going to make more A, right? Okay, you guys hopefully remember that basic idea, and the French chemist Le Chatelier is the first to sort of demonstrate that idea. The question now is, why? Why does that happen? Yeah, put in more B, it just goes that way. Why does that happen, right? And the reason is there must be a potential. There must be an energetic potential. Remember, other than me adding the B in, for example, that rearrangement of the distribution of moles of A and B is a spontaneous process, right? It happens all by itself, other than me shoveling in the B. So where does that potential come from? Well, one way to think about that is, if I take a rock and I lift it up over my head and I let go, it's going to hurt because it's going to hit me in the head. But more importantly, why did it fall? It fell because I raised that mass up relative to the center of mass of the planet up in a gravitational field. And when I let go, the energetic potential drove the rock towards the center of mass of the planet. You take the plug for your laptop, right? You plug it into the wall. Why does your laptop turn on? Does your computer turn on? It's because there's an energetic potential between the electrical circuit in the wall and the circuit in your computer that then draws that current from the wall and allows the computer to work the way it's supposed to. Think back again about my heated rod example. You heat up a hot rod you stick it up to something cold. Heat's going to flow spontaneously from that heated zone into the cooler zone spontaneously because there's a thermal energetic potential. In the case of a chemical reaction like this, it's exactly the same idea. There's got to be a potential that drives that reaction to move the way it does, and it gets a name. It's of course known as the chemical potential. Because we're thinking about chemistry, right? Chemical reactions, and it gets a symbol as well. In the case of this reaction, the chemical potential for reactant A gets a large G, again for the Gibbs free energy, but it gets a little bar over the top of it, and a sub A. And the chemical potential for component B would look something like this. The chemical potential is also known as the partial molar free energy. And it's defined formally with the symbol mu for component I, and it equals the partial derivative of the overall system free energy with respect to the number of moles of component I at constant temperature, pressure, right? And all other components fixed, right? So another way to think about this is that the chemical potential or the partial molar free energy tells you how much a given reactant or a given component, let's say A, contributes to the overall free energy of the system, right? Given how much you've got and what kind of a molecule or what kind of thing it happens to be, right? Like I said, that definition leads naturally to this idea that the partial molar free energy, right, is very clearly related then to the amount of stuff you've got, how many moles of it you've got. And that can formally be written down, and it looks something like this. The partial molar free energy of reactant A, in my little reaction here, is simply equal to G sub A naught. There's the naught, all right? And that's the partial molar free energy under some reference state. We'll come back to that in a minute. Plus, there's the gas constant again, RT, natural log of the amount of A that you've got. Okay, that's great, except for a couple of things. One is that I snuck the naught in there again, but like I said, we'll come back to that here in a second. The other is mathematically, there's a problem with that relationship. You can't take a log of a number that has a unit associated with it. And yet I've written that down like that. And the answer to that little conundrum is the fact that this relationship really only applies formally under so-called ideal solution conditions, which is thankfully where biochemists, physical chemists generally like to try and work when they can. And there's a parameter that's known as the activity. All right. And for my reactants A and B, the activity for A would be lowercase a sub A, and for B, it'd be lowercase a sub B, right? And the activities are the formal way you get around this problem with this logarithm in that mathematical expression. Because the activities fundamentally are unitless. Right? They have magnitude, but they have no units. They're essentially just numbers. But as they're defined, the convenient thing is under ideal solution conditions, right? The activities approach and are essentially under completely ideal conditions with some slight deviation. The activities are essentially equivalent to the concentrations, again, under things that approach ideal conditions, right? So the good thing is you can now rewrite that expression as G sub A. Formally, it would look like this, plus RT log of the activity of A, and the logarithm problem goes away. Okay, well, what about the little naught guy? All right, well, the naught here in G sub A naught, this is the so-called standard state chemical potential of component A, of reactant A, right? Essentially, it's A's partial molar free energy under a defined set of conditions. And you guys may remember from your previous chemistry courses or physical chemistry course that that standard state for most reactants is defined as a concentration equal to 1 molar. And the question then becomes, well, why 1 molar? Why would you pick 1 molar? Why not 2 molar? Why not 3.5 molar? Well, look at something. If you think about 1 molar as saying, well, I'm going to define, because I need to have a reference point. If you look at that equation, it's got to be referenced to something, and that's what we're dealing with, is the standard state. If I say, well, I'm going to make 1 molar concentration be equivalent, right, to the activity of, say, a component, or equivalent to when the activity equals 1. Remember, activities have no units. So now guess what? If you substitute 1 into that expression, what happens? Log of 1 is 0. So under that set of conditions, you would have G sub A equals G of A naught plus RT log of 1. Log of 1 is 0, which means that cancels out. So partial molar free energy in my standard state condition, or in this one activity is 1 molar, is simply equal to G sub A naught. Okay. So now let's go back to that reaction again, my little idealized reaction of A moles of A turning into B moles of B, right? So we want to know how to express a chemical potential change between one set of conditions and another set of conditions, right? So that if there's going to be a change, we know there has to be a change in free energy for everything we've talked about at this point, thinking about spontaneity. There has to be a difference in free energy between 2 different states for something to happen. So we can say, well, that means we've got to be able to calculate a change in free energy, which would be equal to the free energy of the products minus the free energy of the reactants, which in this case would simply be equal to the number of moles of B I've got times its partial molar free energy minus the number of moles of A I've got times its partial molar free energy, right? Well, that's kind of cool, because now I can substitute in this relationship that defines the partial molar free energies. Remember, G of A is going to equal G of A naught, right? Here it is, plus RT log A. Right? Okay. Which means if I do that substitution here, it will look something like this, which is that B times G0 sub B plus RT log, and I'm going to switch back to using concentration of B, even though it's a little sloppy. You chemists and biochemists do this all the time. Just remember that when it's written like this, you basically mean the unitless equivalent, which is the activity, right? Minus A times G sub A naught plus RT log A. All right, that's cool. All right, we're everybody with me? So now we can multiply that through and group some terms. It's going to be B times G sub B naught minus A times G of A naught plus RT log concentration of B to the B minus log concentration of A to the A. All right? Yeah, okay, well that difference, the difference here, right, is simply equal to the difference in the standard state free energy difference here. So that I can rewrite this way as simply equal to delta G naught, right? Now, plus RT, and then applying some laws of logarithms, that just means this expression, the expression here, turns into something that looks like this. RT log concentration of B to the B divided by the concentration of A to the A, right? That's great. That's actually a really, really useful expression, right? There are all kinds of situations, and we're gonna see and use that expression. But think about this: when system is at equilibrium, we know that delta G. I'm gonna do this a slightly different way. I meant to emphasize that the delta G under some set of conditions, right, is equal to that expression. But at equilibrium, we know delta G equals 0. The other thing we know at equilibrium, that is also true at equilibrium, is that the concentration of B raised to the B, that's our products, divided by the concentration of A raised to the A, is equal to the equilibrium constant, recall. Which means the following has to be true. At equilibrium, 0 has to equal delta G naught plus RT log of KEQ. Rearranging that expression, we now get that delta G naught equals minus RT log of the equilibrium constant. Okay, and there's the expression that we started with.